So in this video, we're going to go over working through this problem where we're asked, is the dissolution of calcium hydroxide spontaneous at 298 Kelvin? And so as we go through this problem, we're given some data. So we're given some thermodynamic data, and we're given delta H of formations and our standard molar entropy. Oops, left out the units on that. We'll put that in joules per mole times Kelvin. This is just taken from the back of your textbook. So to start this problem, as always in this type of thing, what we need to do is start off with a chemical reaction. And so we're dissolution, so we're dissolving calcium hydroxide. So we can start off and write the chemical equation, CaOH twice solid, so calcium hydroxide goes to calcium 2 plus aqueous plus 2 hydroxide ions, aqueous. So here's our balanced chemical equation. Now, we're asked to find, is it spontaneous? So in order to answer that, that's really asking what is delta G. And so recall, we have an equation for delta G. Delta G is equal to delta H naught minus T delta S naught. And so to solve our equation, we're going to have to solve for what is delta H of this reaction, what is delta S of this reaction, and then we can substitute into our equation. So we'll start off with our delta H term, delta H of reaction, and remember with all these thermodynamic variables, what we're going to do is we're going to take the sum of the products, and we're going to subtract the sum of all the reactants. We have to make sure we add everything together and really pay attention to signs of things. So our products, we have a calcium 2 plus cation, and we have 2 hydroxide anions. So for this, we're going to have the sum of our products are going to be that calcium 2 plus, which from the table we can see is negative 542.83. And then we're going to add to that, and now note we have 2 hydroxides, so I'm going to do 2 times negative 229.99. And so that would be our products. And then from that we have to subtract. I'm going to subtract our reactants, which is the calcium hydroxide solid, so which is negative 986.09. Okay, and so next what we're going to do is we're just going to plug this into our calculator, and you should be, when you do this, what you should end up with is a delta H of reaction. Please confirm that you can get this number is negative 16.72, and the units on that are kilojoules per mole. So there's our delta H. Okay, so we now have delta H. We're going to do the same process for delta S. And so we're going to have our delta S of reaction. It's going to be equal to, and just like delta H, it's going to be the sum of the products minus the sum of the reactants. But now instead of our delta H values, we're going to be using these delta S values. And we're going to set it up the same. And so we have our products. So we have our calcium 2 plus, which is negative 53.1, plus, and now we have 2, because of our coefficient, times negative 10.75. And then from that, we're going to subtract our calcium hydroxide solid, which is a positive 83.39. And if we do this math, we find out that our delta S of reaction is going to be negative 157.99. Put the units back in, joules per mole times Kelvin. So there we have our thermodynamic parameters, our enthalpy and our entropy of the reaction. We can make some notes on that. So if we look at this, we can say our delta H was a negative value, so that's telling us that this is an exothermic reaction, right? And we can recall that that's a favorable event. It's releasing energy. And we can also see that in this case, our delta S of the system is less than 0, so that's unfavorable. So we have one of our parameters that is favorable and one that's unfavorable. So now that we have our values, we can come back to our delta G equation, and I can plug that in up here so we can see everything. Well, actually, I'll go below. Come down here, we'll say delta G is equal to delta H minus T delta S. And again, watch your units when you do this. We have the units of kilojoules per mole, and then our entropy is in joules per mole Kelvin. So we're going to have to convert one of those. So our delta G is going to be, and I'm going to convert my enthalpy term from 16.72 kilojoules to negative 16,720 joules per mole, minus our temperature of 298 that was given in the problem, Kelvin, times our negative 157.99 joules per mole Kelvin. Notice the Kelvin units cross out, and we're left with joules per mole. And in the end, our delta G is going to be, and I'm going to go back into kilojoules now, 30.4 kilojoules per mole. So this is our change in Gibbs free energy of the reaction. And from this, we can see since delta G is greater than 0, this is a non-spontaneous reaction. So this reaction will not occur at room temperature under these conditions. If we come back here and we ask ourselves, what's going on? Why does this reaction not take place? Why is this a unfavorable non-spontaneous reaction? We can say the enthalpy is favorable. That's an exothermic reaction. So what's actually controlling this reaction is the change in entropy. So the change in entropy of the system is just too great so that we're not able to overcome that at this temperature, right? And so this is going to be overall non-spontaneous. Now, this is one way to solve this problem, but I want to point out a second way where we could go at this problem. And if we look at that Appendix G in the OpenStax textbook, which gives this thermodynamic parameters here, you'll also see a third column there. And that third column is the change in Gibbs free energy, right? So we have this third column, and this is in units kilojoules per mole. And we can look up these values and find out for calcium hydroxide solid, we get negative 898.49. For our calcium 2 plus, we get negative 553.58. And for our hydroxide, we get negative 157.24. With these values in hand, we can actually do a second type of reaction to get to the same answer. So instead of using our delta G equation here, we can actually do our delta G products minus reactants, just like we did before, and go straight to our final answer. So in this case, our delta G is going to be the sum of all of our products. So we're going to have our negative 553.58 plus 2 for the hydroxide times negative 157.24, and then subtract the Gibbs free energy of our reactants, which in this case is negative 898 8.49. And when we go ahead and do this out, you can confirm this on your calculator. You get positive 30.4 kilojoules per mole. And so again, what we see is we're going to get the same answer. Now, two ways to go about things. This second case may be much faster to get there, but what we lost in the process of doing this was the ability to say it was the entropy term that controlled the reaction to make it unfavorable, right? We didn't get the breakdown of those two terms. And the other thing we lost is the advantage of this delta G equals delta H minus T delta S is we could ask the question of, if we change the temperature, what happens to spontaneity? So in this case, we can change the temperature and say, what will the effect be? Or we can figure out at what temperature will this change from non-spontaneous to spontaneous by setting delta G equal to 0 and solving for T. Thank you.